Welcome to this lecture on Bra Ket Algebra. And here I will try to discuss certain properties of Bra Ket Algebra. Then I will talk about operator. Then I will define projection operator and its properties. Then finally I will try to express wave function in terms of position and momentum, right? Or in other words, I can say that I will focus on position and momentum representation of a wave function and how wave function can be described in terms of Bra and Ket vectors. So briefly, let us talk about Bra Ket algebra. So consider a two-dimensional vector space. I'm taking two-dimensional vector space just for the sake of simplicity. And we are having two vectors x1, x2 and x1 prime and x2 prime, and they are related as, say, x1 prime is equal to a11 x1, a12 x2, and x2 prime is equal to a21 x1 and a22 x2. And in matrix form, they can be written as x1 and x2 prime, a11, a12, a21, a22, then x1 and x2. And this can be written in the form of a Bra and Ket notation. So in Bra and Ket notation, they can be written as Ket x prime must be equal to A. A is this transformation matrix or transformation operator. So what does it mean? This means that operator A, when applied on Ket vector x, and changed it to another Ket vector x prime of the same vector space, and another very important thing, that a Ket vector is represented by a column vector. A Ket vector is represented by a column matrix and the corresponding Bra vector is a row matrix. And is obtained by this row matrix corresponding to a Bra vector is obtained by transforming column matrix to row matrix and taking the complex conjugate, of every element, that is bra x is equal to x1 star x2 star row matrix. Similarly, it can be written as x1 prime star x2 prime star, right? And they are related to each other as bra x prime must be equal to ket x, bra x and operated with the operator a, or if I try to elaborate it, x1 prime x2 prime must be equal to x1 and x2, and it is a11 star, a21 star, a12 star, and a22 star. Because a is given as a11, a12, a21, a22. So a dagger is nothing but complex conjugate and taking its transpose, and it is a11 star, a12 star, a21 star, and a22 star, and taking its transpose. And if I take its transpose, so it will become a11, a21 star, and a12 star, and a22 star, right? So that's what we are getting. So if I use it and then try to solve it, that what I am getting, it is x1 star a11 star plus x2 star a12 star, then it is x1 star a21 star plus x2 star and a22 star. That's what I'm getting. And in simple form, it can be written as a11 star x1 star plus a12 star and x2 star, then a21 star x1 star plus a22 star and x2 star. So keeping all these things in mind, we can conclude that if x prime ket x prime must be equal to a into ket x, then x prime bra of x prime must be equal to bra of x into a. Then let us talk about a few properties of ket bras and brackets. Properties of ket bras and bracket vectors, right? I will talk about their properties, very few properties. So first property is a very important property. So corresponding to ket psi there exists a unique bra psi. The another property, so if A and B are operators, if A and B are operators, in general, operators are represented by taking hat over that. So A and B, they can be represented in this manner. So then A operator when operates over psi and B operator operates over phi, then it can be converted into corresponding bra vector by taking Hermitian conjugate of that operator and is post multiplied. Here the operator is pre multiplied, here the operator is post multiplied. And this thing we have to keep in mind. This is a very important thing, right? The next is if alpha and beta are complex numbers, then how they will affect the things. Operator means they are matrices. They can be expressed in terms of matrix form. So if alpha and beta are the complex numbers, then let us try to understand that what will happen. So alpha psi ket can be written as alpha can be taken outside, right? And similarly, alpha psi bra vector, it is alpha star bra vector psi, it can be written in this form. Then next is, say it is psi alpha phi. So here alpha is multiplied with the ket vector. So this number can be taken outside it as it is if it is multiplied with the ket vector. But if some complex number is or any number is multiplied with the bra vector, then it can be taken outside but with the complex conjugate of that number. This is a very important thing which we have to keep in mind, because it is multiplied with the bra vector, so it can be taken outside as it is but with its complex conjugate, right? So it is a complex conjugate of this complex number. And if I take consider bra ket vector psi phi, and if we take its complex conjugate, then it can be written in this form. And if we take sum of this, then it can be written as sum of first and the sum of second. Sorry, first vector with the sum of second ket vector. Okay. Then next property is psi phi. It's a bra vector, it's a ket vector. So it can also be expressed in the form of integral psi star x and phi x, it is dx. So integral representation of a bra ket vector. And this psi 1, psi 2 star phi 1 plus phi 2 star is, phi 2 dx, if it is this one, then it can be written as psi 1 plus psi 2 and phi 1 plus phi 2. And if I operate it, then it is psi 1, it is phi 1 plus psi 1 phi 2 plus psi 2 phi 1, this into this, plus psi 2 phi 2. Then if alpha and beta are two complex numbers, then psi alpha phi 1 plus beta phi 2, say this is the sum of two vectors and taken in ket form, and some number is multiplied with these two vectors phi 1 and phi 2, then they can be expressed in the form of psi phi 1 and psi phi 2, but their constants are taken outside, right? Because these constants are multiplied with kets, not with the bras. So when they are multiplied with bras, then what will happen? So it is basically they're multiplied with the bras. So they can be taken outside separately, but with their complex conjugates. So they are taken outside. So they are very important and interesting properties which we have to keep in mind. And there is another very important property relating to this again. That if alpha 1 phi 1 plus alpha 2 phi 2 bra vector into beta 1 psi 1 plus beta 2 psi 2, then it is modified to, say this is multiplied with it, so it is alpha 1 beta 1. So here alpha is multiplied with the bra vector, so its complex conjugate is taken outside, and this beta will be as it is because it is a bra vector, and it can be written as phi 1 into psi 1 plus this is multiplied by with it. So if it is first of all I multiplied with it, then this is multiplied by with it. So it is alpha 1 beta 2. Here again it is multiplied with the bra vector. Sorry, here it is with the bra vector, so its complex conjugate we have to take as it is. So it is this one. So it is phi 1 and psi 2. Similarly, I will talk about the product of this and this. So first of all, if I multiply with it, then alpha 2 beta 1 can be taken outside. So plus alpha 2 beta 1. Alpha 2 beta 1 can be taken outside, but it is with the bra vector, so it is a complex conjugate of this number is also sitting with it, and it is phi 2 psi 1 plus alpha 2 star beta 2, phi 2, psi 2, right? So that's what will happen, right? Now, in the next, I will take an example of this, and it's a very interesting example. So now, I will take an example. See, consider psi ket, it is minus 3 iota, 2 plus 3 iota, that's 4, and ket phi, it is 2 plus iota, and it is 3 plus 2 iota. These are the two ket which I have seen. Then let us try to calculate. Our purpose is to calculate few quantities. So we have to calculate bra psi, and then scalar product of psi, phi and psi, and then psi and phi. Then we have to calculate ket psi and ket phi. Then phi and psi, bra, their product. Then these are few quantities which we have to calculate. So right, so let us try to find out a solution. So let us consider psi is a wave function, wave vector. It is represented by minus 3i, 2 plus 3i, and 4. And then this phi is equal to 2 plus i, 3 plus 2 iota. What I will do, this bra psi is basically is a corresponding row matrix with all the elements to be complex conjugated. So it is 3i, 2 minus 3i, it is 4, and similarly bra phi can be written as 2 minus iota, 3 minus 2 iota, right? So these are the bra vectors corresponding to every ket. Now next is this phi psi, which is 2 minus iota, 3 minus 2 iota, and it is minus 3 iota, 2 plus 3 iota, and it's 4. The first row, first column, they gets multiplied, and the result will be, if I simplify it, the result will be 12 minus 16 iota. Similarly, psi phi, scalar product of phi with phi, it can be written as 3 iota, 2 minus 3 iota into 4, and here it is 2 minus iota, 2 plus iota into iota, then it is 3 minus 2 iota, 3 plus 2 iota. That's what we have to take, and corresponding to it is 16, 12 plus 16. iota. That's the result which we are getting out of it. And from these two, we can also conclude that scalar product of phi with psi is not equal to scalar product of psi with phi. Then let us try to find out next thing. So if I try to calculate this, and this here it is 3 iota, 2 plus 3 iota, it is 4, and it is 2 plus iota and 3 plus 2 iota, and phi and psi, they can be written as minus 3 iota, this is psi, this is phi. Okay, then phi and psi, the value of the phi will be minus iota 2 minus iota 3 minus 2 iota, and it is 3 iota, 2 minus 3 iota and 4. Now let us have a look at these two. Since it is a column matrix, and the product of the two column matrices is not possible. Similarly, the product of two row matrices is also not possible. So that means these two terms are not possible to calculate, or this product is not feasible. Now let us try to calculate one very important thing. Psi phi. This is ket psi into bra psi, and bra phi. So it is minus 3 iota, 2 plus 3 iota, it is 4, and it will be 2 minus iota 3 minus 2 iota, and if I multiply these together, then what I am getting, it is 3 iota, it is 2 minus iota minus 3 iota minus iota, 3 iota minus and 3 minus 2 iota, and it is 2 plus 3 iota into 2 minus iota, 2 plus 3 iota multiplied by minus iota, and it is 2 plus 3 iota and 3 minus 2 iota, and then 4 multiplied by 2 minus iota, sorry, not 2, yeah, 4 into 2 minus iota, 4 into minus iota, and 4 into 3 minus 2 iota. That's what we are getting. And this, after simplification, will leads to a 3 by 3 order matrix. So minus 3 minus 6 iota, 7 plus 4 iota, and 8 minus 4 iota. And here it is minus 3, 3 minus 2 iota, and minus 4 iota, minus 6 minus 9 iota, 12 plus 5 iota, and 12 minus 8 iota. So this was the result, and this will also be possible. Then let us discuss few more properties. if ket vector psi is said to be normalized if scalar product of psi with itself is equal to 1, then this is known as normalization condition. Then next is the Quartz property or the Quartz inequality. As we know from vector algebra, that A dot P its mod square is less than equal to mod of A square into mod of B square. So in bracket notation, this can be written as scalar product of psi and phi square. It must be equal to scalar product of psi phi into phi into phi. Sorry, here it should be psi, right? Then next is triangle inequality. Triangle inequality, and in case of triangle inequality, as we know from vector algebra, that this A plus B its mod is less than equal to mod of A plus mod of B. And in bracket notation, this triangle inequality can be written as psi phi it must be equal to psi psi under the root into plus psi phi under the, not psi phi but phi into phi. So let me correct it. It is scalar product of phi phi at square root. It is phi plus, sorry, so this is known as a triangle inequality in bracket notation. Then next is, let us talk about the orthogonal states. Orthogonal states, so the psi and phi are said to be orthogonal if their scalar product is 0. So this is the condition for orthogonality. Then let us talk about orthonormal states. So two kets psi and phi are said to be orthonormal if they are orthogonal and if each one of them is normalized, right? So the first condition is that the condition of orthogonality, that means psi phi is always 0, but psi with itself psi is non-zero, is 1, and similarly phi phi is also equal to 1. So these are the conditions for orthonormality, and in general we can write down this condition psi I psi j, and it is equal to delta I j. This is a way that how we will define some properties of orthogonal things. Two vectors which are orthonormal. So now let us talk about operators, its definition, and there are certain properties of these operators. Operator. An operator is represented by some letter, the capital letter and a hat over it, is a mathematical rule that when applied to a ket, psi, it transforms it into another ket psi prime of same space. That means a operator operating over this, it gives me another ket. Similarly, if it acts on bra psi, bra phi, not psi, transforms it into another bra phi prime, that is phi operated with this operator, then it gives us another bra phi prime. Then let us discuss certain examples of operators. Examples of operators. So first of all, let us talk about unity operator. This unity operator, it leaves any ket unchanged. That is, when unity operator operates over psi, it gives us the same ket. Then there is another example, gradient operator. This gradient operator, when operates over psi, Here I'm taking example in the form of a wave function. So del when operates over psi, it is curly over curly x psi r I cap and curly over curly y psi r j cap, or curly over curly z psi r as a k cap, or you can write it as I cap curly over curly x plus j curly over curly y plus k curly over curly z at the psi r. And then linear momentum operator. You studied in detail in BSc classes regarding these operators. So you should go through those books to study these operators and how these can be calculated. So let me talk about linear momentum operator. So if a linear momentum operator is represented p hat, so when it operates over psi, it gives us minus iota h cross del psi r. So this is linear momentum operator. Let us discuss few properties of operators. So when a operator is sandwiched between a bra phi and ket psi, it yields a, or it results a complex number. That means this always gives us a complex number. Say, let us try to understand it in more detail, that how this will happen. So this phi is basically a row matrix with order 1:n, and this if operator is a square matrix. Then it is, let us try to understand, it is n by n, it is n by 1. So first of all, let me try to multiply these two. If I multiply these two, then a resultant will be what? A resultant will be a column matrix. A resultant is a column matrix. So that means this is 1:n and this is 1:n. Their product is basically a column matrix. It is n:1, because they are common, so resultant will be n:1. So this is a column matrix and this is a row matrix, and when I multiply these two, then resultant will be a matrix of 1 by 1. So that means this contains only one element. So what I can say, if phi 1 and a1, phi a and psi, they all are the matrices of complex space, means if all their constituents are the complex number, then their resultant will be always a complex number. This is a way that how things can be analyzed. Then another very important thing which you have to keep in mind, this phi a dagger, sorry, a cap psi, it can be either done in this manner or you can do it other way. So both are the same thing. Means this operator either can operate with this first of all and then with this first of all and then operate with and so on. That means things will not change. So both the results are equivalent and the resultant will not change, or the answer will not change, right? So this is, if you this is a very brief discussion about the operators. Now let us talk about projection operator. Next is the projection operator. So an operator is said to be a projection operator if it is Hermitian and equal to its own square then it is said to be a projection operator. That is, p dagger must be equal to p and p square must be equal to p. So this is the necessary condition for an operator to be a projection operator. And its example is a unit operator. Unit operator I is an example of projection operator as I dagger is equal to I and I square is again equal to I, so that's why it is known as a projection operator. Now the important property of projection operator. The product of two commuting operators P1 and P2 is also a projection operator. So let us try to understand what does it mean. So consider two operators P1 and P2. P1 and P2, and if I consider these P1 and P2, they are the two operators and they commute. What is the meaning of this? The meaning of this P1 and P2, their product is equal to P2 into P1. And they are separately commute, and they are also projection operators separately. That means P1 dagger is equal to P1 and P2 dagger is equal to P2. Also P1 square is equal to P1 and P2 square is also equal to P2. Now we have to prove that their product is also a projection operator. So to prove that, let us consider now this P1 P2 dagger, and it is equal to P2 dagger and P1 dagger. But P2 dagger is equal to P2 and P1 dagger is also equal to P1. That means the product is Hermitian. Product of these operators is Hermitian. That means one condition is satisfied and another condition regarding their squares. So consider the square, and let me simplify this, their square. This is with this, when it is P1 square, and it can be written as P2 square. So P1 square is equal to P1 and P2 square is equal to P2 from here. So that means their square is equal to P1 and P2, right? So that means both the conditions are satisfied. Hence, it is a Hermitian, it is a projection operator. Product is a projection operator. Now let us do one example. In this we have to show that operator ket psi and the bra psi, their product is a projection operator only when this psi is a normalized. So now consider this, as we know that this psi is a Hermitian. If this is Hermitian, that means now taking square on both sides, one condition is satisfied. Now taking square on both sides. If I take square on both sides, not square on both sides, but taking the square of this, then this can be written as so if both are clubbed together, and order will remain the same, it will not affect the results. So this is 1 because the wave function is normalized. Because psi is normalized, if we assume that psi is normalized, then we can say that this condition satisfies. So that means it is Hermitian, as we know. We have chosen it in such a manner. Then their square is equal to itself. That means it is a projection operator. This projection operator if psi is normalized. Next, I will talk about eigenvalue problem and Ket Bra algebra. Eigenvalue problem and Ket and Bra algebra. So, in terms of Ket and Bra, eigenvalue equation can be written as this A operator when operates over ket psi is equal to A psi. Here, this small a is eigenvalue corresponding to operator A when it operates over ket vector or eigenvector psi. That is, psi is A, ket psi is eigenvector. So now let us understand position representation and then we will go to the momentum representation. So position representation. Here I will see that how wave function can be written in terms of integral or ket and bra vectors, or how ket psi can be written in the form of a integral. So consider an operator. Consider position operator r cap and let it be operator of position vector. Operator of position vector simply position. Then ket of position or ket of position. Then I can write down it as R operator when operates over R, it gives the corresponding eigenvalue R small r, right? So this small r is the eigenvalue of operator R. Value of operator R. Also R must be orthonormal and complete. Also this R vector or the position vector or ket R must be orthonormal and complete. So what does it mean, orthonormality and the condition for completeness? So if R prime, its scalar product is equal to delta function, then it is the condition of orthonormality, and this Ri and summation over I, if it is unity or identity matrix, then it is the condition of completeness. Condition of completeness, and this can also be written in terms of integral. In terms of integral, this can be written as, if we are in a three-dimensional space, its integral is equal to I, then it is also the completeness condition. So let us try to look at now the wave function. As wave function is depending upon R, wave function is a function of R. So let me recall psi, ket psi, and I want to incorporate into a position, because it is a function of position. For that, what I will do, I will operate it with the unity operator, but unity operator represents the completeness condition corresponding to position operator. So to incorporate the position into it, what I will do, I will put the value of this position vector, and psi will remain as it is. Right? And let me rewrite is, I can also express it in this form also. So as we know that this R psi is basically psi R. That is, here what does it mean? It means that psi R represent the components of psi in the ket R basis. So thus, to now I can sum up this result as this psi, ket psi is equal to d cube R or it can be written as d cube R psi R, right? So this is a way to look at the wave function. So it is the position representation of a wave function. Also, scalar product can also be seen in this way, that is phi psi, it is phi I psi, it is written as this as integral of d cube r, it's r, it is psi, it can be written as d cube r, this is phi, and it is r psi. So for bra it is written in this form. So here bra is operated with this, and this is the ket is operated with this, so this will remain as it is, but here it will become a complex conjugate. So sorry, there is integral can be taken outside. Now integral can be taken outside of it. It is d cube r, it is phi r, with its complex conjugate it is psi r. So this is a way that how things can be expressed. So this is a relationship between integration and this what we call bra and the ket notations. Now let us look at the momentum representation of wave function. So as we considered the position operator, similarly I will consider the momentum operator. And such that when it operates over momentum ket, it gives us the momentum factor with it, right? And similarly, this P is a P factor is complete and orthonormal. That is P is equal to delta P minus P prime, and TQP is equal to identity matrix. So that means this psi can be written as I psi, I can be taken from here. So if I put its value here, so it is dqp p operator. So this is ket, this is bra, and it is psi. Now it is simply written as dqp this is psi p as we did earlier. So this is the basically, or sometimes it is written as TQP psi p So this is the momentum space wave function. That means psi p is the momentum space wave function. So with this, in this lecture I briefly talked about Bra Ket algebra, and then operators, and then projection operator, and I briefly talk about position and the momentum representation of a wave function. So thanks for watching this video.